Next, we're going to look at an example to determining the rate of change of the atmospheric pressure with respect to time as observed by an aircraft. And to make it a little bit more exciting, we're going to consider a reduced gravity aircraft. So these sorts of aircraft are used to help train astronauts become used to weightlessness of space. So the idea is that the aircraft flies upward at a 45-degree angle at nearly the speed of sound, and then it cuts its engines. So when its engines are off, it travels in a free fall trajectory. So it takes a parabolic trajectory, and then when it returns to approximately the same altitude, so it's basically in a nosedive at about 45 degrees, again approaching the speed of sound. It turns its engines back on and then sweeps out of the nosedive and levels off. So for this entire duration in here, which may last for like 40 seconds or something like that if I remember correctly, inside the aircraft they have basically an empty cabin where the people in there experience weightlessness. And the reason is that the aircraft itself is basically in free fall, and the people inside are in free fall. And so the aircraft and the people are all falling at the same rate. So it's a similar situation as if you have a very tall tower with an elevator in it, and you cut the elevator cable, and then the elevator starts to fall, and there's a person inside. Well, while the elevator is falling, the person is going to appear weightless, right? They'll just be floating with respect to the elevator because the person and the elevator are both falling at the same rate. You can try this at home, not with an elevator, but with a shoebox. You might not want to put small fuzzy pets in the shoebox, but maybe a penny or something like that. So you can hold the shoebox at a very high position, stand on a chair, hold a penny in the shoebox, and drop them both at the same time. And it will look, if you're just looking into the shoebox, it looks like the penny is floating within the shoebox if you forget the fact that they're both falling. Because basically if you're falling relative to gravity, you feel weightless. In the space station, or when the astronauts are in space, this is exactly what gives them weightlessness. It's not the fact that there isn't any gravity in space. So if you have the Earth, let me do a better circle. So if you have the Earth, draw it as like this, and then you have an orbit, something like that. So this is the orbit of a satellite or a space station. If you were to put a mountain or build a tower that was as tall or had the same altitude of the orbit of the space station, which is about 100 miles, so that's about 100 miles in altitude, you could pretty much just stand right on that tower. I think gravity, the acceleration due to gravity is about 90% or more compared to being on sea level. So you're not going to notice a big difference. You could stand on a mountain that was that tall. So you might wonder, well, why are astronauts weightless when they're in the space station? Well, the answer is as follows. Basically, the idea behind an orbit is that your satellite or your space station is in perpetual state of free fall. So imagine if you have this hypothetical mountaintop and you were to launch a cannon, but you don't launch it very fast, and the cannon or maybe it's fast, it's a powerful cannon, but the cannonball is going to do this. It's going to fall and hit the Earth. Let's say you launch the cannon a little bit faster. It's going to go like that, right? So it's going to fall and just eventually crash into the Earth. If you launch the cannon fast enough, as it falls, an interesting thing happens, right? So this is the path of the falling cannonball. Every time the cannon, so let's do a close-up. Here's the mountain, here's the Earth. Every time the cannonball drops in altitude by 1 meter, the Earth's surface below it also curves by 1 meter. So moving forward, you're falling, and as you fall by a distance of 1 meter, the Earth's surface has curved to be a meter away farther from you. So you're not any farther away from the center of the Earth than you were before, even though you're falling towards the Earth. So you can do this calculation. The speed necessary to achieve this is approximately 18,000 miles per hour. And that's how fast the space station goes, and that's how fast the space shuttle goes in order to get into orbit. So the space shuttle, when it was active, was pretty astonishing. It went from 0 to 18,000 miles per hour in about 8 minutes. I think maybe 8.5 minutes. So an enormous acceleration. During those first 8.5 minutes after launch, it travels over 1,000 miles. It reaches an altitude of 80 miles. So if you think about a standard aircraft reaches an altitude of 35,000 feet, which is maybe about 7 miles tops. The space shuttle reaches an altitude of 70 miles, and it reaches that altitude within like 3 minutes. And then during those first 8.5 minutes, it travels a distance of over 1,000 miles. Well, it's accelerating from 0 to 18,000 miles per hour. The astronauts feel, I think the peak acceleration is something like 3 Gs. So the astronauts will feel 3 times their body weight being pressed into the seats during that bumpy ride into orbit. So that's basically a little bit on why you have weightlessness in space. It's not because there's no gravity there. To the contrary, gravity is about as strong as it is on Earth, maybe 90% of the strength. But you could still stand on a mountain if you had a mountain that high. But it's because the space station is in a perpetual state of free fall that astronauts float, because it's the same as being in an elevator car that's falling towards the Earth, and you're in the car, you're falling towards the Earth as well. So relative to the car's frame, if you can't see outside of the elevator, you just think you're floating in the elevator car, and of course, until of course you hit the ground. But for the space station, you never do hit the ground because they're going fast enough horizontally that when they fall 1 meter vertically, the Earth's surface curves 1 meter vertically beneath them. So they're always at the same altitude. So with these reduced velocity aircraft, it's the same deal. You're in the aircraft, and then you're in free fall, floating within the aircraft as the aircraft goes up and then starts coming down. So since it's just in a state of free fall, it doesn't matter if the velocity is upward or downward, it's still just a state of free fall that gives you 0 velocity. So let's say that the atmosphere pressure can be modeled as, well, it is modeled, P0 e to the minus h over h0. So h0 is a benchmark altitude, and this is 7,000 meters. It's basically the altitude at which pressure is a factor of 1 over E times the atmospheric pressure, and that happens at about 7,000 meters. Atmospheric pressure is 101.3 kilopascals. And then for our particular aircraft, let's say that h of t is 9,500 plus 122.5 t minus 4.9 t squared. For the state. And to find out how long this is, basically at time 0 we're at an altitude of 9,500 meters. So the question is, at what time will we return to an altitude of 9,500 meters? We have an initial upward velocity of 122.5 meters per second and a downward acceleration of 9.8 meters per second squared, which is divided by 2 for this term. So if we set this equal to 9,500, the 9,500s cancel, and we get 122.5 t minus 4.9 t squared is equal to 0. Factor out a t. So the second time at which h of t is equal to 9,500 is when this is equal to 0. So t is equal to 122.5 over 4.9. And that's after 25 seconds. So this will go for, t on 0 to 25 seconds. So this gives us the altitude as a function of time. This tells us the atmospheric pressure as a function of altitude. So what we want to determine is the rate of change of the atmospheric pressure with respect to time as viewed by the aircraft. So that's going to be dp dt, and that's essentially dp dh times dh dt. Right? This is the same as saying, p of h of t, so the derivative with respect to time is p prime of h of t times h prime of t. So p prime of h of t, since h is the independent variable for this p function, this is dp dh times a dh dt. So dp dh is, we just take the derivative of p0 e to the minus h over h0. But it's an exponential function, so we rewrite it. And then we multiply by the derivative of the exponent. So the derivative of minus h over h0 is minus 1 over h0. Right? Because minus 1 over h0 is just a constant times the variable h. So dp dh is equal to this. And then dh dt is going to be 122.5 minus 9.8 t. So this gives the vertical velocity of the aircraft as a function of time. So to find out the rate of change of the pressure with respect to time, it's going to equal minus p0 over h0 e to the minus h over h0, and then times 122.5 minus 9.8 t, where this h up here is understood to be, so h is equal to 9500 plus 122.5 t minus 4.9 t squared. So if you want to express dp dt only as a function of time, you would replace h with h of t. But this basically tells you the rate of change of the atmospheric pressure per unit time. So it tells you the kilopascals per second. And so if you have instrumentation on the aircraft, it tells you how quickly the pressure gauge in the aircraft is moving as the aircraft performs this sort of maneuver. Now, since its vertical velocity is greatest at the beginning, we would think that dp dt is greatest at the initial time. And I'm not 100% sure about that because we also have this factor here. So let me clear some space. And let's write dp dt up here. So dp dt is minus p0 over h0 e to the minus h of t over h0 times 122.5 minus 9.8 t. So let's plot dp dt as a function of time from 0 to 25. So basically, let's do a plot. Let's say p of t is equal to, so we have minus 101.3 divided by 7,000, or we can do it in pascals instead of kilopascals. So that way the thousands cancel out. And note that that's the same as 101.3 divided by 7. So pascals per meter is the same as kilopascals per kilometer. So let's just think of this as pascals per meter. Exponential, so minus 9500 plus 122.5 t minus 4.9 t squared over 7,000 times 122.5 minus 9.8 t. And then let's plot. This is actually dp dt. So let me change the name of this dp dt. So let's plot dp dt. T goes from 0 to 25. Okay, so initially, dp dt is about negative 450 pascals per second. So I use pascals and meters here. So it's going to be approximately a half a kilopascal per second decrease. But halfway through the flight, we're at the highest altitude, which is the lowest pressure. So the pressure stops decreasing and starts increasing. So dp dt goes from negative to positive. And then this maximum at 25, the pressure is increasing at, again, about a half a kilopascal per second. So that is the model for dp dt as a function of time over that maneuver.